Hi, I'm Guoyuan An. I'm from Korean Advantage Institute of Science and Technology. It is my great honor to attend this conference and introduce our work, GraphShop, graph-based approach for shop type recommendation. My co-authors are Song-Yi Yun, Ceyun Kim, Lin Wang, and Myung-Ho Kim. First, what is shop type recommender system? Let's think about this scenario. You have found a good business place, and you want to open a new shop there. It might be a coffee shop or a restaurant. Now you have to consider a lot of factors to decide which type of shop to open. Available capital, earning ratio. One of the most important things here is how popular will shop type be in this place. Shop type recommender system is trying to solve this problem. It aims to predict the popularity of a shop given its type and location. Let me give you an example. This is a region near my school, KAST. There are two universities in this region. In front of these two schools, there is a river and a subway line. Now, we think the place near the two schools and the place near the subway station might suit different type of shops. But it is hard to say what exact type do they suit and how popular will each type be. We want to make a quantitative level analysis. Here, I introduce some previous works on shop type recommender system. Generally, we will first divide a city or district into many small regions, and we think these three regions might get more influence from the universities. These three regions are near the subway station, and these three regions are more like the residential regions. After we divide them into several regions, we use the collaborative filtering to solve this problem. Basically, collaborative filtering thinks if two people share same interest, in this case, this girl and this boy share same interest, then they should like same items. If this girl like all of the 4 fruits, this boy might also like all of them. Similarly, in shop type recommender system, if two subway stations, Y station and G station, have some same characteristics, then shops in Y station might also be popular in G station. But this kind of methods meet some challenges. You might ask, how about the shops located at the border of two regions? In this case, the available place is in region A, but clearly it is more close with the coffee shops in region B. So this area might be a good area for coffee shops. Even if two locations belong to same region, they may share totally different neighbor shops. It seems like this part is good for hamburgers, and this part is good for stationery. So what should we do? We think one of the solutions is considering the distances among shops. When we connect shops using edges, it looks like a graph. Intuitively, we might give a better solution if we could regard shops as nodes in the graph and consider their relations. To do that, let me give a new definition for this problem using graph concept. V is the vertex set, and every shop is represented as a node here. E is the edge set. It recalls the distance of every two shops. Because all the shops are logically connected with each other, this is a complete graph. We record the features of each shop, the average price, popularity, ratings. T is the test set of all possible types. Here, the problem is, Given a shop location and a type, we want to predict the popularity. We want to use graph neural network to calculate the embedding vectors of node V and the type T, and then use recommendation method to predict the popularity. We propose a novel GNN framework called GraphShop for the shop type recommendation. This is the overview of GraphShop. It consists of two modules, the time module and the distance module. Time module tackles the complex interactions between different types, and distance module aggregates neighbors' information from very far distance and analyze their relations. I introduce the distance module firstly. This is a target shop. There are many neighbors around the target shop, but we don't know which neighbor shop is influence its popularity. Intuitively, we think if the faraway shops are influential, then they will first influence the shops here. Then all of them will influence our target shop together. This process is very similar with the recurrent neural network, so we use RNN to learn the diffusion process. Instead of studying shop-to-shop relations, we study the interzone relations and keep the characteristics states of the far zone if it influences shop's characteristics in the near zone. However, how to deal with intrazone relations becomes a new challenge, considering the shops in a zone are unordered. Inspired by the point net, we designed the aggregating block, which uses the MLP function and the symmetric function to approximate a continuous set function. That is, the perturbation in the set will not greatly change the approximated function value. In addition to distance, the interaction relations among shop types is another critical factor. When predicting the popularity of the target shop, the information of similar shop types is more valuable than unrelated types. We present type module to give different weights to different types. Given a target type, the neighbors share similar types should get larger weights. We apply the CNN layers to aggregate properties of shop types in the type-based ordered graph. The previous works collected data from review websites and map applications, but the datasets were not publicly open, so we followed their instructions and collected our own datasets. Compared with existing shop datasets, our dataset has the following benefits. First, concentration. All the shops in our dataset are located in 5 districts in Beijing. Beijing has 16 districts in total. Second, a more massive amount of data. Our dataset incorporates the information of more than 50,000 shops in total. 3. More variety of shop types. Our dataset includes 122 shop types. We use mean square error to measure the closeness of the predicted popularities to their ground truth values. Following the previous works, we use the comment number to represent the ground truth popularity of a shop. The experiment result shows that GraphShop outperforms traditional matrix factorization method 40% and outperforms the basic GNN method 16%. From the ablation study, we show that both distance module and time module works well independently, and combine these two modules, we could get a better result. In conclusion, we increased the performance of state-of-the-art technique by 16% on popularity prediction task. We also constructed and opened a new large dataset. At the future work, we need more experiments about how far and how many neighbor shops to consider when predicting the popularity. Also, more data should be collected and analyzed, such as each shop's profits, the nearby institutes, and people's flow. Thank you. If you are interested in our work, please check our paper and our project website for more detail. Our dataset and code are also available in our project page.